Our first speaker of the afternoon is David Archer from University of Chicago. He's been there for about 20 years. He's professor of geosciences there. He's an expert in the carbon cycle, his interaction with the global climate. He's written numerous books, including The Long Thaw, How Humans Are Changing in the Next 100,000 Years, Global Warming, Understanding the Forecast, and most recently his PUP climate book, The Global Carbon Cycle. And he also does his bit for educating the youngsters, and every year he teaches a class which reaches over 500 students at the University of Chicago. So, David.
So when Ingrid Gnerlich first approached me to do this book, I sort of had the feeling like I was done with trying to write books to save the world, because I was just, my stamina for this was kind of running low. But what really got me was when she showed me the list of the other authors that she'd recruited for this series. It's really a club that I just couldn't pass up the opportunity to be a member of if it wanted to have me. So, and it turned out to be a really fun book to think about and to write. The audience for it should be the same as for the rest of the books, you know, sort of climate wonks or aspiring climate wonks, not geochemists in particular. And I had the same sort of problem, you know, issues to think about as Dave Schimmel mentioned about ecosystems, that the carbon cycle is not really just one field. There's land people, there's ocean people, there's paleo people, and that, you know, they're big enough fields that we don't really all know each other. And to try to summarize all this stuff into a sweet little package is a fun challenge. And in the end, I ended up, this is the table of contents from the book, I ended up doing it according to time scales, because the carbon cycle has fundamentally sort of different personalities when you think about it on different time scales. So to start with, the longest time scales are sort of 1 million years and longer. And that's chapter 2 after the obligatory kind of gratuitous intro chapter there. So on the geologic timescales, the CO2 concentration of the atmosphere is controlled by a thermostat mechanism that has to do with the carbon cycle. So the cycle here is kind of to and from the deep solid Earth. You have degassing of CO2 to the atmosphere, and then the CO2 is consumed by reaction with igneous rocks. This is a shameless oversimplification of the chemistry of an igneous rock, showing you just the part that's important for us. In order for this to dissolve, it needs to take a CO2, and then that's deposited as calcium carbonate in the ocean, and it's subducted, and it gets cooked and turned back into igneous rock and CO2 again. And the part about this that turns into a thermostat is the weathering reaction here. How fast you can dissolve rocks depends on how much water you're splashing over the rocks, the hydrological cycle, rainfall and runoff, which depends on the temperature of the Earth. So if the Earth is too warm, you'd be weathering too quickly and you'd pull the CO2 down, and so it turns into a nifty thermostat mechanism. So if there's perturbation, such as this event 55 million years ago documented in sediment cores, not clear where this carbon came from, but it was analogous to sort of pedal to the metal global warming climate event, something like thousands of gigatons of carbon coming from someplace, going into the atmosphere and warming things up. And then the CO2 thermostat sort of cleaned it back down again on a time scale of 100,000 years sort of thing. And this is what we expect for the fossil fuel CO2 as well. So this morning you heard Professor Vallis talk about the fact that CO2 released to the atmosphere will stick around for centuries and centuries. Well, that's sort of 3/4 true, but 1/4 too simple. The after CO2 is released to the atmosphere, there is this sort of quick drawdown as it equilibrates with the ocean and the terrestrial biosphere. So it's sort of spreading out among the different reservoirs in the fast carbon cycle at the surface of the Earth. But after it's finished equilibrating with the ocean has had its fill, there's still some carbon left in the atmosphere. So there's this long tail, which actually, as we've just seen, the thermostat takes 100,000 years or something like that to operate. So, and it makes a big, I mean, this isn't the majority of the CO2, it's about 10, 20%, but it's, if you think about slow reacting parts of the climate system like ice sheets or methane hydrates or permafrost, it makes a big difference if it's going to go away in a few hundred years or whether there's this long tail. So saying the lifetime is hundreds of years is kind of like saying Chicago is a couple miles away. It can lead you, it could lead me to the conclusion that I could have walked here this morning, but that would have been fundamentally wrong because it's just not the right, just not right. So this is the result of an intercomparison project. All of us who do this kind of modeling subjected our models to a slug of CO2, and then this is what happens to them. Some of them come down faster than others, and there's some wiggles here. But none of them get anywhere close back to the original CO2 value by the time the end of these simulations at 10,000 years. So there's no scientific controversy, but there's this strong tendency among scientists and in the popular literature to say that, to sort of oversimplify this and lose the long tail. So there that is. Now, just because the weathering thermostat is controlling the CO2 on long time scales doesn't mean that the CO2 is always the same or the climate is always the same. There can be things that change the thermostat setting, if you will. So one very interesting idea from John Edmonds is that the calcium carbonate system in the ocean today is extremely out of steady state in that there's much more calcium carbonate landing on the seafloor and accumulating there than there is going down in subduction zones. And that's because there's much more carbonate in the Atlantic, and most of the subduction is in the Pacific. And that's sort of it makes sense to us because as the ocean crust gets older, it gets denser and more prone to sinking. And if it's denser, it also makes a deeper ocean, and you have less calcium carbonate under lots of water than if you have sort of topographic highs in the ocean. But on the longest time scales, the system has to balance. You can't be putting more on the seafloor than you're taking off forever. And so the last time that shallow ocean sediments subducted, then to supply CO2 to the atmosphere to warm everything up, was when India was crashing into Asia, and the Tethys Sea, which is a shallow seaway with carbonates, had to get out of the way. So that was a warm time in Earth history. Another possible change to the thermostat setting that people talk about is mountain uplift. Because when you raise mountains, you make them much easier to weather. The soils all kind of wash off, and the rocks get ground down into flour. Glacial rock flour ice is a tremendous erosion agent. And this makes it easier to do the weathering that pulls the CO2 out of the atmosphere. And another thing people talk about is land plants, which started to develop in the Silurian. They pump CO2 down into the soil, and also decaying plant material is down in the soil. So actually, if you go out and measure the CO2 concentration in soils, it's much higher than the CO2 concentration in the atmosphere, 10 times higher. And that tends to make that dissolution reaction, the weathering reaction, happen more quickly. So it's like, so that allows the CO2 concentration to be lower and still accomplish the weathering. It changes the setting of the thermostat. So the next part of the book shortens the time scale to talk about the glacial interglacial cycles. And here is totally different because, as we talked about this morning, the carbon cycle is acting as an amplifier of the climate changes which are being driven by the Earth's orbit around the sun. So there's a clear physical link between how much sunlight you have in the summertime in the north where all the ice sheets are or could be, and the volume of ice. But then what you find is that in ice cores, when the orbit says, let there be more ice, then somehow the CO2 says, yeah, I'm going to go down and amplify that climate change. So that's what makes the climate change probably more global. That's why the whole world goes into an ice age at once, because of the carbon cycle. And so it's acting as a positive feedback, an amplifier on this time scale, rather than a negative feedback. And this was a hard chapter to write, because we don't really know what's going on. Answer to your question, Andy. And it's hard to write a sweet, succinct little chapter when you're basically clueless, right? So, and it's probably, you know, the hardest chapter in the book to read. There is this very tantalizing link between the rise in CO2 at the end of the last ice age and the Southern Ocean. The North and the South, they do this sort of seesaw thing in terms of temperature. So the South started to warm first, and then it warmed up a bunch in the North, and the South got cold, and then the North got warm, and the South got anyway, back and forth. And Antarctica is kind of not the global average in this. Antarctica is kind of the weird part of the rest of the world, sort of looks more like the North. But the CO2 very clearly follows the patterns from Antarctica, not the patterns from the rest of the world. So there's evidence of a deep, stagnant water mass, low in C14, very salty, and it's sort of, it appears as though the C14 concentration of the atmosphere is dropping at the same time as the CO2 is rising. So it's tempting to look for some stagnant blob where you can put a lot of radiocarbon, dead carbon, because it's very old, and then lots of CO2 in it, and then let it come out at the end of the ice age. And there's some sediment cores that have these spikes of a very old C14 as if they're catching a whiff of this stuff going past. But the mass just doesn't add up. You can't come up with a volume of the ocean and reasonable changes in its chemistry that can account for the C14 and the CO2. And there's other things that are going on, we know are happening, that would change the CO2, but it's not very clear how much they're changing the CO2. So those factors include possible changes in the pH of the ocean, or in biological production, or the solubility of CO2 in a colder, deep ocean. But none of those are big enough to really explain the whole thing. And the hard part, I mean, you can make a model that doesn't actually cheat. I said you had to cheat a lot to make this work, and that's not really true. It can be done, but you have to line up all of the ducks in a row exactly right in order to make it work. It just doesn't seem very likely that a cacophony of causes could lead to such a brilliant, beautiful correlation between ice volume and temperature as is seen. So I find it sort of unsatisfying. One really cool idea that I heard from Lowell Stott, I don't know if it's right or not, but it's the kind of thing that I'd put my money on at this point. He says that there are lakes of liquid CO2. This is stuff coming out of the Earth, volcanic CO2. Not very big today, but they're observed. And he says that during the last ice age, the temperature of the deep ocean was colder enough that you're just starting in this blue curve here to get close to the zone where CO2 hydrate might be stable to make a bigger lake of liquid CO2 down there. And that would, of course, be radiocarbon dead. And he thinks he would need about 1,500 gigatons of it to explain the C14 and the CO2. You know, it seems to me like we need a blast from outside. We're stuck. We can't, the ocean just doesn't, in my opinion, doesn't do it. And the unfortunate implication of that is that it's impossible to say if in the fullness of time the ocean in the future will respond as a positive feedback to our own climate change or not. So the third chapter in the book is about the present and future carbon cycle, and we've seen, the stabilizing geologic carbon cycle and then the destabilizing glacial interglacial carbon cycle. Well, what are we going to get for the future? And as we heard this morning, today, in the last decades, hopefully the next couple of decades at least, the natural world is helping us out by taking up CO2. So atmospheric CO2 is only rising half as quickly as it would if we were, if the natural world was not doing that, going into the oceans or into the land biosphere. But on the longer time scale, is the ocean going to turn into a positive feedback? It sort of depends on what the mechanism was that led to the feedback in the past. If it's Lowell-Stott's liquid CO2, then maybe it's blown all of the CO2 it has, and warming it won't cause the ocean to release any more. If it's something to do with ocean pH or biology or something like that, maybe it could be a positive feedback in the future beyond a few decades or centuries or something. And then there's other reservoirs too. There's lots and lots and lots of carbon in soils, especially in permafrost soils, which are thawing. And there's methane in the hydrates. And so on the long time scale, there's lots of room for the carbon cycle to see it be an amplifier of climate change. There's a chapter on methane, which I call the radical wing of the carbon cycle. It's hot because methane, being a less abundant gas, has a disproportionate effect on the greenhouse forcing per molecule. A molecule of methane is worth 40, 50, 60 molecules of CO2 in terms of its greenhouse forcing. Fortunately, methane has a short lifetime in the atmosphere. If you release methane to the air, it doesn't stick around and accumulate like CO2 does. It has a lifetime of a decade or something. So I want to show you this model that I did for my class of methane. This is not in the book. But so I have heard the claim that the Arctic could release 50 gigatons of methane on a short time scale. So we're going to put in a 50 gigaton methane spike, and we're going to say that it happens all at once. And you see the methane concentration goes up, and then it comes down over a few decades. But the interesting thing I want to show you here is the radiative forcing from the methane, which is the red line, which follows the methane concentration. It goes up and then comes down in a few decades. The green line now is the radiative forcing from business as usual CO2. So not worst case, one in a 1,000 kind of possibility, could happen, oh my gosh, but business as usual, what will happen unless it changes. And so you've got the green curve and the red curve. If I had to choose, I would take the red curve, because then we get it all at once, and then it takes a while for climate to respond. So the methane would be subsiding before the climate really got spun up, and things would always also be improving with time. So we could ship wheat around for a few decades until things started getting better. Whereas CO2, we're getting trapped into this thing. It's only getting worse. The trajectory is not better. It doesn't get better. It just, unless you start removing CO2 from the atmosphere, which is something that could be done. But, so the worst case methane scenario that everybody's hyperventilating about in the press is actually, I think, better than business as usual for CO2. So yeah. Well, right. Yeah, but just sort of to compare them, there they are. And, so if we got clobbered with methane, maybe we'd, come to our senses about CO2 a little quicker. Bring it on, yeah? I have, I don't know, maybe a third of the pages in the book are these little boxes, which are sort of self-contained with the more technical stuff. If you don't really want to learn about alkalinity or pH chemistry or something, you can read the main narrative of the book and skip those boxes. And there's one that I wanted to show you just because I've never shown this to anybody before in a talk, and the reviewers were too polite to mention it, and I was astonished that Ingrid let me keep it in the book. It's called the carbon cycle orrery. So an orrery is a model that they made of the solar system to sort of predict the movement of the celestial bodies before they knew about Kepler's law and ellipses and all of that. And so the orrery was made with, things, it was mechanistically incorrect, but they tuned it to give you the right answer. So this is an artist's rendition of my orrery here for the carbon cycle. It has to do with, I use this analogy in my class a lot of a kitchen sink, and you turn on the water and the water level rises in the sink until it finds a value at which it's going down the drain as fast as it's coming in from the faucet. So the weathering thermostat, I use it for that. It's the CO2 coming out of the earth would be analogous to water from the faucet. And then weathering is the water going down the drain. It depends on the water level. The way the weathering depends on the CO2. It's a sort of negative feedback, catch-all analogy. Well, so this one, I've got these 3 tubes representing the carbon chemistry of the oceans. This is dissolved carbonic acid. Here's bicarbonate, which is where most of the carbon is, and here's carbonate ion. And the CO2 thermostat, here's the CO2 in the atmosphere. So the CO2 thermostat is represented by water sort of dribbling through that. This is degassing from the earth, and here it's dribbling out there, and so it's going to try to find the level at which those things balance. And then this is connected to that, and everything's sort of connected together. So the way a fossil fuel event would go is first you put a bunch more water in this atmospheric CO2 tube, which causes it to equilibrate with the ocean. This is the part that takes a few hundred years. And so then after a few hundred years, the CO2 dissolved concentration in the ocean is higher. And then these things are mounted on a balance beam, which I call the pH balance. So here's this thing, the whole thing can swivel, and it's got a little indicator here which points to what the pH value of this ocean is. So when you put more CO2 in, it makes it heavier on that side, makes it dip down, and now both the CO2 and the carbonate ion side are higher than the bicarbonate, and so water is flowing from both of those tubes into the middle tube. So that's kind of sort of like the way that the buffer chemistry of the ocean helps the ocean to absorb CO2 by reacting with the carbonate ion. It's not really mechanistically the same, and you could, change the tubes to be, get different sort of behavior, so it's like an orrery, not like a... And then you've got, there's also a similar drip, drip, drip thing going on with the carbonate ion here. Stuff comes in, drips, and then it comes out. This has to do with the calcium carbonate system. So if you have less carbonate ion than some critical value, it'll tend to build up, and that's the way calcium carbonate works in the ocean. The calcium carbonate system will neutralize the acid of the fossil fuel CO2, for example. And you set this thing up so that this one goes faster by about 10 times than this system. So when you neutralize the fossil fuel by depleting the carbonate ion concentration, that means you don't get as much calcium carbonate burial, and then that will get restored by the drip, drip, drip through that side, and ultimately the calcium carbonate system can be seen to be buffering the chemistry of the ocean. So I don't know if this was illuminating to you or not. If not, you can just be polite about it if you want to. Or tell me that, I shouldn't have put it in the book, but there it is. And so that's my book. Thank you.